Okay, so we looked at cases where the sound wave or light wave or whatever kind of wave reflects off of the boundary, but what happens to the portion of the wave that actually goes into the new boundary? And that is a concept called refraction. So this is when a wave strikes a boundary between two mediums. So we'll just say when a wave strikes an interface. The wobbliest boards. So it strikes an interface. A portion of the wave travels into the new medium. Now here's something to note. When a wave enters a new medium, its wave speed and wavelength will change, but the frequency will stay the same. Okay? When a wave enters a new medium, the wave speed and the wavelength will change. But the frequency stays the same. And that is going to play out with our wave equation. If my wave speed goes up, my wavelength is going to go up. This is going to remain constant. Okay, this remains constant. From medium to medium, the frequency stays the same. It's these two variables that will alter accordingly. Okay? Another thing to note is that if a wave strikes a medium at a 90-degree angle or strikes an interface at a 90-degree angle, it will pass through undeflected. So if a wave strikes an interface at a 90-degree angle, or just head on, it will pass through undeflected. If it strikes it at an angle, we tend to see a change in the direction. Not tend to, we see a change in the direction of the wave. Okay, and we'll kind of talk about that in a moment. So, when the light wave goes into the new medium, how do I know what the new wave speed, the new wavelength is going to be? And that is defined by a property called index of refraction. So this is kind of like a measure of the optical density of a material. Oh, I could write a little neater. And the symbol for it is the lowercase n symbol. The equation for it is that n is equal to c over v, where c is the speed of light in air. Very fast. It is 3 times 10 to the 8th meters per second. So this is how we could determine the change in the speed of a wave, the speed of a light wave, as it goes into different mediums. Two values that we just use a lot in physics are the n value for air, which would just be 1, because it would just be c divided by c, which is just 1. But the other common one we use is for water, and that's 1.33. So there is I think a table of n values in your textbook that you could refer to determine what the speed of light is in a given material. So this is how you can figure out the change in the speed. We're not going to go into it so much in this unit, but if you wanted to know, like, how does the wavelength change? The wavelength in a medium changes by dividing by the n value. So if you just took the wavelength of the light in air, I'll qualify that, The wavelength of light in the medium is just the wavelength of light in the air divided by n. Now with this, we get something called Snell's Law. That's a fun one, huh? Snell. So Snell's Law basically looks at how light changes direction as it goes into a new medium at an angle. So this is a relationship between the index of refractions in two mediums and the angle at which light is traveling through those mediums. I don't know if it has one L or two L's, and I'm not going to worry so much about it as I was a physics major. Sorry, I'm not sure. That might be a spelling error. The angle at which light is traveling in those mediums. So the relationship is n1 sine of theta 1 equals n2 sine of theta 2. That is Snell's Law. Whenever we do Snell's Law, we're in degree mode. To give you like a little visual of this, let's say I've got my interface. So this is my medium 1. This is my medium 2. So like this is N1, N2. And I've got my ray of light. And it strikes the interface at an angle. This would be my theta 1, this would be my theta 2. And it's a way to determine what the new direction of my light wave is going to be as it travels into that new medium. Okay? It's a pretty straightforward equation, and we'll practice it when you get back into class, and then we'll do a lab on it, okay? Okay, so this is an example of using Snell's Law. So just a reminder, Snell's Law is N1 sine theta 1 equals N2 sine theta 2. And our angles are measured with respect to the normal, and when we are doing our calculations, we need to be in degree mode. So this says a ray of light is approaching the boundary with water at an angle of 52 degrees. Determine the angle of refraction. So in this problem, it doesn't say what the initial medium is, and usually if it doesn't say it, it's assumed that it's air, because air is all around us. So here I have air, here I have water, here's my light ray, and that angle is measured with respect to the normal. So this right here is 52 degrees. And my question is, what is the angle at which it is going into the water? And so it's pretty straightforward, just plugging in using Snell's Law. N1 sine theta 1 equals N2 sine theta 2. So 1 times sine of 52 is equal to 1.33. Remember, that's the n value for water. Times the sine of theta 2. And you would get out your handy dandy calculator. You would actually calculate this. You'd say 1 times sine 52 divided by 1.33. Well, that's a terrible marker. And then you get a value for sine theta equals some decimal, and then you would inverse sine that, and you get theta 2 is equal to, I got 36.33. So, kind of in terms of the drawing, undeflected would be like this, where this would be 52 and this would be 52. But this angle, we just calculated, this angle is 36.33. So instead of it being there, the angle is actually like, I totally didn't draw that well. I need a ruler of science. That's a little better. So there's my angle of 36.33 degrees. And sometimes we refer to this as bending towards the normal. Like this is my undeflected ray, but it is being refracted and it's going into a more optically dense medium. So it bends towards the normal, okay? If it were to go into a medium that was not as optically dense, then it would bend away from the normal, okay? Now, with Snell's law, when you go from an index of refraction, air was equal to 1, water was 1.33. When you're going from a low index of refraction to a high index of refraction, the light ray bends towards the normal. But if you go the other way, if you go from a high index of refraction to a low index of refraction, it bends away from the normal. And I want to kind of give you that visual here. So I'm going to go the other direction, and we're going to see this concept of what's called total internal reflection. So I'm going from water into air, and if I hit it straight on, no angle, my light ray actually just goes undeflected, okay? But if instead I hit it at an angle, here's my normal, my light ray bends away from the normal. And as my angle of incidence increases, so as this angle increases, my bend away from the normal is also going to increase. And that's going to keep on happening. It's going to keep like bending further and further away until we reach what's called the critical angle. And for the critical angle, how many markers? For what's called the critical angle, the angle of refraction is 90 degrees, okay? So that's something called the critical angle. There is a particular angle for a light ray going from a high index of refraction to a low index of refraction where the light ray doesn't actually make it out. It just refracts along the surface. And any angle above this critical angle will just result in reflection. Because for each of these points, like some of the light ray gets refracted into the new medium, and some gets reflected back, and some gets reflected back, and some gets reflected back. Well, for this one, that's all. We only get reflection. Nothing refracts into the new medium. Okay? So that concept is called total internal reflection. So this is when a ray of light goes from a high index of refraction to a low index of refraction. Actually, this is the equation. I should write down the concept. So, when a ray of light travels from a high index of refraction to a low index of refraction, it bends away from the normal. Okay, and hopefully you have a visual of that now. At the critical angle, okay, when theta 1 is called theta C, that's the critical angle. The theta 2, or the angle of refraction, is 90 degrees. And any theta 1 that is bigger than that critical angle will result in light just being reflected within that first medium. So any theta 1 that is bigger than the critical angle will result in the light just being reflected back into the original medium. So being solely reflected back. Into the original medium. So no light refracts into the second medium. So this is this idea that, like, if you're looking in water, and normally when you can see in the water, it's because something in the water is emitting light. That light is coming up from the water into the air. And if all of a sudden, like, you step and the angle changes and you can't see that object anymore, like all you see is like a smooth reflection, like a mirror-like effect, the reason is the light that's coming from below is hitting beyond that critical angle, and that light is not making it out into the air. So when that theta 1 is equal to this critical angle value, theta 2 becomes 90 degrees. And so if we think about, if we should look at the mathematics of it, we actually can get a relationship to figure out what that critical angle is. So here's Snell's law. N1 sine theta 1 equals N2 sine theta 2. What I'm saying is, when theta 1 is this critical angle, theta 2 just becomes 90 degrees. And the sine of 90 is just 1. So we actually have a relationship that, I should have put theta c there, sorry. That N1 sine theta c is equal to N2. It's more commonly written that sine of theta c is equal to N2 over N1. Okay, and again, this can only happen if N1 is bigger than N2. This only happens if the light is going from a medium of high optical density to a medium of low optical density. Okay, so that's how we can actually figure out what the theta c is for a particular interface. So let's look at one example of this. This says, what is the critical angle for light traveling in water and going into air? So it's traveling in water, so here's my N1 of 1.33. Going into air, that's N2. Oops, I don't know why I wrote equal again. N2 is equal to 1. So in this case, here's my relationship. Sine of theta c is equal to N2 over N1. So sine of theta c is equal to 1 over 1.33. And again, you'll use the inverse sine function to figure out your theta c. And if you pause the video, calculate it out, you should get that your theta c value is 48.75 degrees. Okay, so that's the critical angle for light going from water into air. If it hits that interface at anything bigger than this angle, then that light will just get reflected into the water and it won't make it out into the air.